All right, good morning, everybody. Welcome to class from home. Well, a lot of you are already used to this, but now I get to teach full class from home. I had to set my home computer up for all this now, which means hopefully my machine is a little bit more reliable than the one from school. We'll see. Say that, and now I probably doomed it. All right, well. Before anything bad happens, let's get to it. We are continuing our discussion of triangles this week. We've got a few new features to investigate for today. The triangle inequalities. Okay, set this up. Remember last week with the Pythagorean theorem. We said not only can you use the Pythagorean theorem to find the third side of a right triangle, you could use it backwards, basically, to test if something was in fact a right triangle, and that's pretty handy. Now we're going to generalize that a little bit. We want to see what is the test to see if something is a possible triangle in the first place, let alone a right triangle. Can we even make any triangle? You go walking through the woods and you pick up 3 sticks. Can you put them together to make a triangle? This might be more important in like a survival, build a shelter kind of situation. Okay? But practically speaking, construction, right? A lot of buildings and things are based on building up triangles. Remember, everything digital, computerized, 3D animation is all made out of triangles. So you got, okay, what size of triangles can we use? Can we make this fit? Can you make it into a triangle? So what I have for you here is a set of sticks of various lengths. And I want you to examine them closely and let me know if the following combinations could make a triangle or not. So in the chat, yes or no, will 3 different colors of sticks be able to make a triangle? What do you think? Can I build a triangle out of a green one, a red one, and a blue one? Or this even includes green, red, and the large blue one down here. We got 1 vote no, 2 vote yes. More votes for yes. It's looking pretty good, right? What I gotta do here is I gotta grab this line and hold on. I need to make sure I do this in a way that it doesn't change the size, right? So I want to link this up there, maybe rotate it around. Can I fit this in place? And grab with the short guy? Okay, not right there, but you can see that this is going to work, right? I can meet those up pretty easily. So with the short one, yes. How about with the long one? Let's see. I bring the green down here maybe, build off of it that way, and then the red one. I'm a little off screen there. Yeah, that's pretty close, right? We can agree. I got close enough. I'm not gonna waste your time fiddling with my device here to get it exactly perfect. But I think we can see now that yes, that's definitely going to work. Let me get them back into position there. So 3 colors, yes, it will work. What about all blue? Yes or no in the chat. Can I make a triangle out of the 3 blue ones? Well, that's 3 votes for no so far. 4 votes no. Anyone think yes? No? Alright, watch this. Y'all are about to be proven completely wrong. I can take this guy and match him up there and stick him on the end, and then I take this guy and we'll give him a tilt and tap him onto the end, and then I just need to get these 2 ends to oh snap. Okay, you guys are right. Yeah, that was an easy one, right? Yeah, there's no way these can form a triangle because these guys are too short. They can't reach in the middle there. They've got to be longer. And so we can see from this somewhat extreme example, there is definitely a bound, right? There is a limit of some sort on the sizes, relative sizes of the sides of a triangle. If these 2 sides are too short, right, they won't meet up when they attach to the bigger one. This is too big to make the rest of the triangle. Okay? And that's the general consensus. Imagine, if you will, taking those lengths and laying them on top of each other, just as I've done here. If these 2 points can meet, if they meet exactly in the middle, careful there. Let me make another set of colors here. Okay, if they meet exactly in the middle, pretend I can't make them touch without it being one line. Oh, I could do a different color. How about that? Let's put an orange one here. Right? Oh, it even snaps into place. Look at that. And exactly the same length. Right? If they're exactly the same length, right? 2 sides add together to be the same length as the 3rd side, you still don't have a triangle. Right? Because now they would lay flat on top of each other. You need just a little bit more so it bumps it up a little bit. So you get that little bit of an effect. Come on, give me the rotating thing. There you go. Right? That pops out there. That pops out there, and you actually get a little bit of a slope to your roof. Right? That's what you need. That bare minimum, just more than. And of course, you can go beyond that. You can make them longer and longer, so long as, like, this one doesn't then become longer than these 2 combined, right? Which brings us to our general rule for the triangle inequality. I often see this as the sum of the other 2 need to be greater than, but I think it's easier to focus on the biggest side. No single side may be equal to or greater than the sum of the other 2 sides. Okay? So if you were to call them sides A, B, and C, A cannot be greater than B plus C, right? Not greater than. Equal to or greater than. Include that. Not equal to or greater than the sum of the other 2 sides, because then it's too big. They won't be able to match up. And that, of course, applies to all of them. B cannot be greater than or equal to A plus C. And C cannot be greater than or equal to A plus B, right? All of those have to be true. You got to check any one side. And usually you check the most extreme, right? You find the longest side and compare that, or the shortest side and compare that to see if it's too short. Right? So that's one version of the triangle inequality. And this is called the triangle inequality, right? The one that makes triangles happen. Are there any questions on this concept? Okay. Again, I think the visual makes it very clear if you were to have actual physical objects of that. Numerically, you're going to have to check these sums, right? And usually you can see this. Your brains are such that you add things together almost instantly, okay, by instinct. You can look at it and be like, 42 compared to 711, like, oh, yeah, there's no way, right? You could obviously see that this one is way too big sometimes. Maybe once they get a little bit closer to each other, okay, double check, okay? Add a couple things up and compare. That's all you got to do there. Now, the other triangle inequality has to do with within a given triangle, as it exists, how would you compare the smallest and the biggest? And that's the unequal part. When we're setting, we would say, what's the largest to smallest angles and sides here? I think my pen's a little too large for this. I can look visually here, and I can see that side A should be the largest, right? So I can say that side length A is greater than, looks about, B greater than C, right? So this is not enough to make a conclusion about any particular length. I'm not estimating, oh, it's about 12 centimeters or anything like that. This is maybe they're closer to, I can't quite tell if something is equal to, okay? I'm not making that judgment, okay, because there's no tick marks, right? They didn't tell us that like this is supposed to be equal to that. So it looks to be about in this order. And what's interesting about that is once you put the sides in order, that automatically tells you what order the angles go in, because the largest side will also be across from the largest angle. And the smallest side, in this case C, will be across from the smallest angle. So that one's going to go last, and then we put B in the middle here. And that holds up no matter the triangle. Let me clear some of this out of the way. I should be able to grab and manipulate that guy, right? So as long as angle A is the biggest angle, right, side A stays the biggest side. But as soon as I go past it, like this, oh no, right? Now angle B is clearly the largest angle, and so side B, we can see now, is also the largest side, right? If you get your position extreme enough, it becomes fairly obvious. Now down here, it looks like I've got almost possibly an isosceles triangle, okay? And that's where things break down, is when you look at, oops, laser pointer please, thank you. Right? If this side looks about equal to that side, well, now I'm going to replace this and say A is equal to B. So I can't quite sort them in largest to biggest order. I don't have enough information. Visually, it looks too close for me to make that call. But I can, however, still mimic the angle measurements here, right? It's still quite clear that angle C here is the teeny tiniest angle in the triangle. And A and B look fairly similar to each other. I'd say maybe A is still a little bit bigger. Look at it real close, but right? That's going to be a tough call. Which one is the biggest? They look about equal. And if they are equal, if these sides are equal, then the angles are equal. In fact, that's a property of isosceles triangle. So it still holds up. The smallest side is across from the smallest angle. The largest angle is across from the largest side. That's the takeaway here. That they go in order. As the sides go, the angles go. And as the angles go, the sides go. And you can sit here and you can play with this, right? and confirm that to yourself. If I make any of these bigger than the other, okay, we can make side B be the biggest. We can make side C be the biggest by going out here. Right? Anywhere I go, if C is the biggest angle, C is the biggest side. Right? A is the biggest angle, then A is the biggest side. We can see that that's going to hold up no matter how I move this guy around. Okay, confirm for yourself, right? Anywhere I move this, even this like extreme little sliver here, A is by far the biggest angle, and A is definitely still the biggest side. Okay. So any questions then on that concept? No? All right, so your practice for today. Up here we've got, right, testing, is it possible to draw a triangle with the given measurements? Right, so this is where you have to check, okay, not possible, right, no, make a sketch. Your demonstration sketch is going to end up looking like, probably like these blue guys here, okay? So draw something like this, except label each one, be like, okay, this is the 14 centimeter, and this is the 28 centimeter, right? That's your sketch, to show that there's too big of a gap between these ends for it to fit. Okay? And you're just testing, can any two of these be combined, or is any one of them bigger than the sum of the other two? You gotta check each combination there. And 4 through 6 is where you're using that second property, right? The smallest is across from the smallest. So looking at number 4 here, I can see the side lengths are given. I know 20 compared to 18 and 13. This is the biggest side. So from those measurements, I know absolutely that angle B across from it must be the biggest angle, right? That's what you're using there. And similar, go ahead and try number 10. Okay, that's somewhat of a challenge question. Make use of that isosceles. You're going to try to identify why, what you know about angles being across from each other and the biggest side, this has to be bigger than that. And you find that PQS must be isosceles, right? Is there a justification for it here? 11 and 12 require compass and straight edge, so we are skipping those, right? Ignore 11 and 12 at the bottom of your page. Otherwise, 1 through 10, totally doable. 10 is your challenge question, but I want everyone to give it a shot. All right? Final call for questions. No? All right. Then, before I let the YouTube stream go, quick reminder, I posted a video just yesterday explaining all the end of the semester stuff and your opportunities therein. So if you haven't already, please go back and watch that. You can read through the video description. Has it all in text form if you prefer. Otherwise, I leave you the rest of the period to work.